Hey, so today we are going to solve this problem, word break. Here we are given a string and a dictionary of words. We have to tell if this string can be made out of these words. So basically, if we can divide this string in such a way that each and every word after the division that we have got is part of the dictionary. So we will be using dynamic programming to solve this, but first let's see a brute force solution which aligns with backtracking recursion. So what will be our strategy? So let us say we are going to partition this string into two parts, and for each and every part we will figure out whether this can be a sentence made out of those words in the present in the dictionary, and on the right hand side also similarly, if this is a sentence that can be made out of those words. If both of them are true, then our answer is true. So this is how we will be proceeding. So let's quickly write down the algorithm. So boolean is possible. String is, we will need an index, and then we'll need our dictionary. Okay, so what will be our base case? So we'll directly check if dictionary dot get the string, if it's present, then we directly return true, right? Then we have to start partitioning our string. So we are currently at index I, so our loop will begin from index I plus 1 till the last. So this j is actually representing where the substring should end. So our substring should begin from I plus 1. So if this is I, so it should begin from I plus 1, and it should go till the last partition that is possible, right? So the value becomes s dot length. So this way the last partition will be cats and dog, and then s. So one more thing that you can see here is that since we have stopping our partition but just one step before the last letter, so that means that never there be a case where this s is an empty string, so we don't need to handle that. Okay, now let's move forward. So left partition is s dot substring, which is from I to j, and right is s dot substring from j. Now we recurse. So let's say possible. So possible is possible left and is possible right. If it's possible, then return, otherwise go ahead. So this is our brute force. As you can see here, we are exhausting each and every partition, but there is one slight modification that we can do in this algorithm. So what we are exactly doing is, for example, if we talk about this partition. So if we talk about this partition, we have two partitions here. So what we are doing is we are recursing for the left hand side, and then again we are recursing on the right hand side. But if you think about it, do we actually need to recurse on the left hand side? Why do we not need? Let's see. So we definitely are doing two things here. First of all, we are checking whether the word itself is present in the dictionary. If it's not present, then we are recursing on the left hand side, and then again on the right hand side, and then what it means is we are trying to break it and see if after breaking if it's possible. So on the left hand side we do not need these two steps again, but this step we still need it. Why is that? Because we have already calculated this info already, that if it can be broken, the left hand side can be broken, and a word can be formed out of that. For example, what I mean is if we have this partition and then we are again trying to break it over and over again for all the partitions that are possible, if this condition was true, that if it could have been broken, for example, let's say we were able to successfully break it at C and at sub. So if these two partitions were possible, then we would have got the value as true, right, in this recursion. But if this was possible, then when the I was at 0, when we were at C index, then itself on the right hand side, on the recursion on the right hand side, that would have given us a positive result. But since we did not get the result, that means that this is futile. So we do not need to consider this case. So that is the reason that for the left hand side, you do not need to actually recurse. What you need to do for the left hand side is only see if it's present in the dictionary or not. So I can remove this and I can instead write is present in dictionary the word lift. So this is one modification that we did, seeing that we do not need to backtrack towards the lift. Now let's quickly find out what is the time complexity of. So let's find out the time complexity. So when you're trying to find the time complexity, always think about the worst case. So the worst case is that you are exploring each and every partition at every index. So basically you are not getting the answer. So that will be your worst case. So let me write this function as Tn. For the first recursive call, the I is 0 and n is the length of the string. So we are going to traverse how many times? T of n minus 1, then T of n minus 2, then T of n minus 3, till T of 1. I can write this as T of n minus 1 as T of n minus 2 plus T of n minus 3 plus T of n minus 4 and so on. So simple substitution in the previous statement, it gives us that T of n is twice of T of n minus 1. Now how can we write this? T of n minus 1 will be twice of T of n minus 2. T of n minus 2 will be twice of T of n minus 3 and so on. It will be till T of 2 is twice of T of 1. So if you think about it, how many times have we written this? So this is 1 to n minus 1. So this can be written as 2 raised to power 0. So see, if we have to multiply the complete statements on the left hand side as well as the right hand side by 2 raised to power 1, 2 raised to power 2, so here it will be 2 raised to power n minus 1. So why are we doing this? So that we can cancel with the previous terms. So this complete statement is being multiplied. So this will cancel. This will also cancel. So on. So f1 will be cancelled. And what will remain is T of n is equal to 2 raised to power n minus 1 into 2 of T of 1, which is 2 raised to power n. D of 1 is constant only. So we have derived that the time complexity is actually exponential 2 raised to power n. So now let's think of how we can optimize this. So for optimization, we can definitely use memoization, but there is a key that we need to observe here, that this recursive function is always returning the answer that is possible towards the right or from this index onwards. So in the starting, if you give 0, so it's telling that the answer towards the right from 0 till the end, if that is possible. So if I is here, again it tells whether from this till the end, if it's possible. So the optimization can be done by using memoization, but we need to see or observe a key thing here, which is that this recursive function that we have written, it receives the index I, and it always returns whether it's possible to form a sentence from the ith index for the ith index till the end of the string. So for example, if I is at this point, so it tells whether nd and dogs, whether it's possible to form a sentence with these letters. So it's always talking about from I till the end. So we can use a simple 1D array for our memoization. So let's say we can have boolean, which is, let's call it D for dp. So what will be the initial values for this? Since we are looking for a possible solution, so we are not interested in the true cases, we are only interested in the false cases. So whenever we have figured out whether it's not possible, we need to store it. So here we can put d of I as false, and here we can check if d of I is false, return false. So this is assuming that this is initialized as true for all indexes. So we have memoized our solution, but after this memoization, what is the time complexity? How much have we reduced? Let's figure that out. To understand the time complexity of our solution with memoization, I'll take an example. Let us say we have this string, and if we were to apply our algorithm, how will it break? It should break like this. Then for each of them it should break like this, and here again it should break for B. So our recursion would go something like this. First we get here, then we get here, then we get here, and then we get here. So if you think about it, so the first value that we are going to put in our DP array will be the last one, that is for B. Then we will put it for AB, then we will put it for AB, and then finally for AAB. So for the very first iteration of our initial value, by the end of the very first iteration, that is the first partition, we would have already filled the complete dynamic array that we are storing the values for. So in the first iteration only, we have found all our possible answer values for this array, right? So let's try writing the time function. So t of n will be, we're recursing for the very first index, that is t of n minus 1. Then we do not need to recurse anymore because we already have found all the possible values, and then we can use our memoization array. So it will be n minus of 2. If you still have confusion, so see, for this n is equal to 4, we found, we traversed or we recursed only for the first index, and for the remaining, that is 2, we can calculate it from our array, right? So for t of n minus 1, it will be t of n minus 2 plus n minus 3, and so on. T of 2 will be t of 1 plus, it should be whatever is the value minus 2, so that should be 0. So how many values have we got till now? So these are actually n minus 1 values. So directly subtract these. So what we get is t of n is n minus 2 plus n minus 3 plus n minus 4 till 1, which is of the order n square. So this is how we prove that for our memoization, the time complexity is of the order of n square. Thanks for being with me in this video. I'll see you next time.